Have you ever wondered how scientists decode the hidden language of materials? Like, how do they connect the invisible architecture of a polymer membrane to its ability to conduct ions? Today, we're diving into a groundbreaking study that uses advanced math and imaging to unlock these secrets. And it's all about hydroxide ion conductivity in anion-exchange membranes. Let's start with the basics. These membranes are the unsung heroes of clean energy technologies, like hydrogen fuel cells. Their performance hinges on how efficiently hydroxide ions, O-, can zip through their structure. But here's the catch. Predicting this conductivity has always been a shot in the dark. Traditional methods relied on vague assumptions, like this material might work better because it's more hydrophilic, but this study took a different path. They turned to Bayesian sparse modeling, a statistical technique that acts like a scientific detective. Instead of guessing, they analyzed the chemical makeup of polymers, focusing on atomic-level details like the distribution of carbon and fluorine atoms. Think of it as building a puzzle where only the most critical pieces are kept. Every feature is tested for its true impact on conductivity. Here's the breakthrough. The researchers discovered that the spatial arrangement of hydrophilic, water-loving, and hydrophobic, water-repelling, regions in the polymer directly dictates ion mobility. But how do you translate that microscopic dance into numbers? They used transmission electron microscopy, TEM, to capture high-resolution images of the material's nanostructure. Then they extracted features, like brightness, contrast, and spatial frequency patterns, that describe these domains. For example, they calculated the mean brightness of the image, how much the brightness varied, and even the kurtosis, a measure of how sharp or flat the brightness distribution is. But the real game changer was breaking down the images into frequency components. Imagine tuning a radio. Low frequencies capture broad patterns, while high frequencies reveal fine textures. By analyzing these, they uncovered hidden clues about the material's structure. Now here's where the math gets wild. The team applied Bayesian linear regression to determine which image features actually mattered. It's like a statistical detective story. They tested which features best predicted the material's composition. And guess what? 3 frequency-based features, HH, SP2048, and SP128, emerged as the top performers. What do these mean? High-frequency features, like SP128, likely capture the fine details of small hydrophilic domains, while lower frequencies, like LL, show the bigger picture. The results showed that the ratio of carbon atoms in hydrophilic versus hydrophobic regions directly influenced these patterns. When there were more carbon atoms in the hydrophilic areas, the domains became more flexible and interconnected, boosting ion conductivity. Conversely, rigid, carbon-heavy hydrophobic regions fragmented the water-loving areas, hindering performance. But here's the kicker. These image features didn't just add new info. They redundantly captured the same structural information already hinted at by the material's composition. This means scientists can now predict a material's performance without complex chemical tests. It's like having a shortcut to understand how a material will behave based on a single image. So next time you hear about breakthroughs in energy materials, remember, the secrets are hiding in plain sight, waiting for the right tools to uncover them. By combining advanced imaging with smart math, researchers are turning complex puzzles into clear answers. And that's how we move closer to a greener future. Thanks for watching. If you want to dive deeper into how data science is reshaping materials research, hit that subscribe button. See you next time.